When it comes to whether a motor has passed or failed, many times we overlook the data and simply rely on the tester. Previously we said we cannot do that. The tester will not trip and fail a test unless the result exceeds a preset threshold. If the insulation has deteriorated enough, the tester will fail a test. However, we hope to provide a test frequency that allows us to see the deterioration prior to the degradation reaching that point. In most mills that means testing critical motors every year. Upon completing this lesson, you should understand how to monitor results as we test, how to review data following a test, and how to analyze results to determine whether a failed test is real or possibly a false trip. A line-to-line resistance test looks for resistance imbalance between phases. If a large imbalance is identified, the motor should be investigated. Typical problems include hard shorts between winding and core iron, hard shorts between coils or turns, either within the same phase or between phases. If new winding, coils wound with incorrect gauge wire, loose or corroded connections, and open circuits. Common opportunities when performing the resistance imbalance test is to ensure proper setup of the test parameters. Use the max delta from average divided by average formula. The default equation calculation can have a significantly higher result. Be sure to select the correct temperature scale when entering the motor winding temperature. This is important for the tester to accurately calculating the corrected copper resistance. Be sure if entering in degrees F the F is selected and not C. Also enable the temperature correction and correct it to 25 degrees Celsius. Copper is corrected to 25 degrees Celsius, not 40. 40 will be used for insulation temperature correction later when performing the insulation resistance measurement. If the parameters are set correctly, this test is more of a pass-fail test. If the 3% threshold is exceeded, the tester will trip. Another important setting is winding configuration. Either Y or delta. Motor winding configuration should be confirmed so that calculations are performed correctly. The test compares the resistance between all phases of the winding. We are checking the integrity of these internal connections as well as the lug crimping and bolted connections in the wiring box. Connecting any leads to the motor, whether you are testing from the starter or the motor, we must be sure that the connections are secure and have good contact. The low resistance Kelvin leads use both sides of the clip. The 4-wire Kelvin leads use an active current source to reduce the effect of test lead resistance. This gives a more accurate measurement than when using the high voltage leads. If any clip connection is compromised, expect an error in the measured resistance and the test will be flawed. After measuring between lead 1 and 2, it moves on to leads 2 and 3. And then L1, L3. If the tester does indicate an imbalance, do we automatically accept that result? We can confirm an imbalance by simply switch tester leads, retesting and seeing if the result follows the tester or stays with the motor. This motor has very low resistance measurement and the difference is approximately 0.00003 ohms, which for this tester may be a stretch. If I do get this result, I would definitely swap the tester leads and compare this result to another test. And this test may continue to fail due to the very low values and the resolution of the tester. Imbalance with readings this low need to be carefully examined before accepting. And may want to retest using a 10 amp low resistance ductor or digital low resistance tester. There are 3 ground wall tests that we use to interrogate the ground wall insulation resistance. MEG for 60 seconds, pi for 10 minutes, and the step test. To perform accurate temperature correction, we need to select the proper insulation type. Thermoplastic is an old version used pre-1975. Thermoplastic compensation formula is 50% reduction per 10 degrees Celsius. Thermosetting compensation formula uses 2 calculations that pivot at 40 degrees Celsius. Normally we will be selecting thermosetting for this setting. When testing ground wall resistance, what do you believe are the effects of water to the resistance of the insulation? Should water affect the overall MEG result? When there is no path for surface leakage and the insulation is in good condition, water will not drive the insulation resistance low. In fact, some owners require new rewinds to pass underwater high-pot testing. Motors that have this requirement should not be impacted negatively from moisture and humidity until degradation of the insulation occurs some years later. Moisture does demonstrate a characteristic when testing good insulation. Moisture causes leakage current oscillations due to the polar charge of water molecules moving back and forth. Movement of charge is also known as current flow. The presence of water also increases the effective surface area of the insulation relative to the ground plane. This causes the capacitance to increase. The Harry current is caused by the polar nature of water. That movement of charge, current flow, is not through the insulation. So, when a good sealed winding is wet, we should expect the MEG ohm measurement to still be high but expect to see leakage current oscillations during the pi test. This shows all the different paths for current to flow when testing ground wall insulation. Conductive current as well as capacitive currents. Capacitive charging should go away quickly during the test. When the winding is wet, the capacitive component stays and is ever changing throughout the test. A pi trend when water is in play, leakage current oscillates, and MEG result remains high. These next 2 trends are more indicative of a contamination path through the insulation, which is not acceptable result. Leakage current is erratic, not just oscillating. In other words, there is spacing between the swings. And the second trend shows constant current flowing either through the insulation from damaged insulation or around that insulation due to surface leakage. Here is a good insulation system. It does indicate slight effects from moisture. I can see some oscillation in leakage current. It is important to look at the current scale. A larger scale will mask the oscillation, and you will not see the moisture. Here the oscillation is about 0.2 microamps. Not the best MEG result, but the pi test is a success. The trend is a bit flattened. Compared to an excellent result, the leakage current is higher and therefore MEG result is lower. Although not the best result, there should be no problem continuing with high voltage testing. We can accept this result even though the pi was below 2.0. Here is a great result and indicates some moisture. Notice the current swings are more of an oscillation and not erratic up and down movement with space between the movements. Oscillation and erratic movement are 2 different things, and they mean 2 different things. We don't want erratic movement. Oscillation indicates moisture, but erratic movement can mean the insulation is trying to break down. Here are 2 examples again of the different signature. One is oscillating and other is erratic. Erratic has some spacing between swings. Additional example of moisture with very high insulation resistance value. Pi ratio is above 2.0, the trend does indicate some surface moisture. This is not indicative of a contamination path through the insulation. I don't see erratic movement. Example of moisture effects with somewhat lower insulation values and a bit of curve flattening. Undesirable result, mainly due to the flattening, indicative of a contamination path. Further testing should be done with close monitoring and stopped if insulation becomes more unstable. Raise flags so that mill understands the risk to further test. The erratic behavior here is not as obvious and may be largely due to moisture. But the combination of the swinging trend and the flattening of the trend and somewhat lower insulation values makes this test undesirable. Use caution if you elect to perform high voltage testing. This motor did not meet the 100 meg minimum after 60 seconds and should have failed the meg. The leakage current curve shows a very erratic trend, indicative of a contamination path or insulation breakdown. This is indicating an unhealthy path to ground is present somewhere in the circuit. This example is not an indication of moisture, although moisture may be present and affecting the circuit. Notice the pi result passed. But this was not a good result. Pi graph shows a very flattened current curve and significant leakage current level, most likely indicative of a contamination path either through the insulation or around it. If megohm reading is below 5000 megohm, consider this motor contaminated. If this is at the motor, I would not perform high voltage tests. A successful step test is when we do not exceed 1000 microamps of leakage current. The meg result does not drop below 100 megohm for induction and 250 megohm for synchronous. The tester does not see a micro arc, the leakage current does not become erratic, and the leakage current end of step is linear with linear steps in voltage. Our goal is to identify motors that are near the end of life, that are in the nose of this curve dash. Great result, linear end of step trend. Somewhere on top of life curve. Intervals are great. This test was not successful. The end of step trend was nonlinear. Indicated ground wall insulation weakness. The leakage current was erratic during the last step, which was indication the dielectric was near the test voltage. So, we can determine from this the point on the life curve to be just above the 9360, which is the full target voltage. No need to surge test this motor. You have already found what you are looking for. This motor will need to be replaced. Nonlinear result with difference between steps doubling indicates severe insulation degradation. Test should be stopped. Also, notice the erratic current in the final step. Any indications of erratic current during the step voltage testing should also be grounds to stop the test. This example could easily be missed. Needed close review of trend. Very easy to overlook. This example could easily be missed. Needed close review of trend. This motor failed in service. Difference in leakage current steps. 0.49 to 0.08 equals 0.41. 0.90 to 0.49 equals 0.41. 1.60 to 0.90 equals 0.70. Next step 2.7 to 1.6 equals 1.10. Next 3.1 to 2.7 equals 0.40. The motor failed on overcurrent. When this abruptly happens as shown here, there is an arc which has degraded the insulation further. This motor did not pass a meg test after this failed step test and had to be changed. The motor failed under test. This was the motor. When we opened it up and saw the pluggage and understood how the winding had been abused and overheated. Question: was this a success story where the testing program was successful? Or was it a story of a failed testing program? Did the tester fail a good motor? Or did it find a compromised motor? This was a success. If we hadn't found the condition of this critical motor, it could have failed during the next time it was started. This was a very wet motor. If we attempt to high voltage test a wet motor, we risk possibly damaging the motor A. The oscillations in leakage current cause an invalid step test. During the step test, the end of step current is captured at end of 60 seconds. The current can be in an upward swing or a downward swing. The end of step plot will be all over the place. No way can we expect a linear result. Therefore, before high voltage testing severely wet motor, we should dry it out. During the pi test, the polarization current will decay because dipoles have aligned. When the tester is automatically running the tests, it advances from the pi to the step test without discharging the winding. If after the pi test, we discharge the winding and then perform the step test, the polarization current will begin again, and that current will add to the charging and conduction current of the step test. This will continue until all dipoles are again aligned. This will result in a trend that resembles this one. Notice the selected test has no pi result, which tells us more than likely the winding was discharged prior to the step. This is more a factor with testing large motor windings than when testing smaller windings. This is same motor same time, only this time we did perform the pi prior to the step. Therefore the windings began the step while charged and no absorption current impacted the step result. Something else we noticed, however, there is a somewhat rounding of the end of step plot. Here, we can see the rounding of the end of step plot. The difference between steps are 0.32, 0.15, 0.13, and 0.10. Not quite linear steps even though the intervals are not increasing. What causes this? With each step in voltage there will be a charge current and an additional polarization current. The increased voltage is again pulling on the free electrons and the dipoles, causing more alignment of the dipoles. This rounded curve is an indication that the charge current has not completely decayed before the 60 seconds runs out. Therefore, the end of step trend is not accurately showing conduction current. This can happen when are testing motor circuits with high capacitance. 60 seconds is just not enough time to allow the capacitive charge current to dissipate prior to plotting the end of step point. Here is a motor with high capacitance circuit tested first at 60-second intervals and second at 90-second intervals. Click. The first trend is rounded, and the second trend follows the straight line. So, this motor requires the tester to be set up for a 90-second interval between steps. If I see rounding, I always increase the time and retest. Surge test detects insulation damage between turns. If there is weakened insulation and the voltage is high enough, there will be an arc produces between the wires. The tester identifies this by observing a change in surge waveform. The pulse-to-pulse test pulses the same phase and compares last waveform to the previous waveform. A line-to-line surge test compares waveform of one phase winding to another. If rotor is installed, the rotor influence will affect the inductance between phases. So, a pulse-to-pulse is only test that we can run if rotor is installed. The graph shows what the final waveform at target voltage looks like. Each color is a different phase. You can see there is a difference in ring frequency between the phases. Each phase waveform has a slight difference in frequency. This motor was tested with the rotor installed. Remember, during a pulse-to-pulse test we are comparing one phase to itself, so we don't care about this slight difference between phases. During the PP surge test, the waveforms are compared to each other to see if there was a change in ringing waveform frequency. A shift to the left indicates a change in ringing frequency. The larger the span between turns, the larger the shift to the left. As shown in picture provided by Megger. Turn to turn slight shift, coil to coil more shift, phase to phase large shift, and a good result. There will be no change in ringing frequency. Over time, the execution of the surge test has changed. Earlier versions of software and before compensation modes, the results were somewhat difficult to interpret. You can see from this EAR graph that for some reason the initial waveform comparisons had more error than latter comparison. There was a ramp that began at the start of the test. Sometimes the early pulses would actually exceed the trip threshold and trip the tester. Sometimes folks though this meant a bad motor. Megger has since corrected these issues with later version software revisions and compensation modes. It is best for any user to always run the latest software revision. Currently it is version 4.8.4.629. Megger also recommends running compensation mode 1 when surge testing. I feel comp mode 1 and 3 are the better ones. Again, an error calculation bug from earlier version software. Megger says this was more an issue with higher voltage motors. This test did include comp mode 2, but the software version was not up to date. If we do experience a surge test trip on EAR, before condemning the motor we should study the surge waveform graph. We can open the window for the waveform and ear graph and enlarge the waveform graph using the enlarge button. If the test did trip, there will be a fourth waveform displayed, which is the failed waveform. We can compare the previous waveform to the failed waveform ourselves to see whether this was a shift left, or something else. Remember, the test is simply comparing area of the two waveforms. If amplitude is sufficiently different or anything is, the test will trip. Here we see the failed waveform did indeed shift left. This is an indication of a weakness in the turn insulation. This pure failure on phase B is not due to a problem with the wave stability and everything to do with how PP ear is calculated when it is turned on. This is due to running an earlier version software. The failed wave backs this up, as there is no frequency shifting noted in the failed wave as compared to the last good wave, and there is only shift in amplitude upward as expect from the next pulse. Review of the EAR graph indicated large pulsing of all phases during the entire test. This is an indication of capacitors or arrestors installed on motor. Need to disconnect those devices and test again. This can also be indication when rotor is being turned while test is underway. A single pulse does not indicate a lower severity concern. This is indicating instability in the waveform, which could be related to a copper-to-copper insulation weakness. In this case it might be turn to turn. The peak happens later during testing. This means either the weakness is deep within the winding and not as likely to be influenced during the switching surge, or that the weakness occurs at a higher voltage. If this is real, we would want to change out of this motor as soon as practical, especially if the motor is critical to operation. How do we know it is real? We cannot study the waveform because that graph only shows the last waveform and not all waveforms. Only way to study this to see would be to lower the trip threshold to below pulse level and retest. If trips, we can then compare the failed waveform to the previous waveform. Earlier versions of software required raising the trip threshold to prevent tripping early from the initial ramp. So, when they ran this test, they did not trip. Even though there were multiple pulses on the EAR graph, no one noticed, and the motor was passed. Because the tester passed it? This motor failed with a few hours after testing. We must always look at the EAR graph following a test. Any EAR pulse needs to be evaluated. A pulse must be considered an issue unless proven not. Just keep in mind that all pulse-to-pulse EAR spikes and especially failures are indications of search wave instability. The further left a spike occurs is a better indication of severity than the level which the spike obtains. Although large percentages could be indicative of phase-to-phase faults or ground faults which would cause a significant shift in waveform. Looking at the surge waves in this case could aid in understanding if those conditions are present. Is this a turn-to-turn fault? Removing the other leads helps. This P2P EAR shows no issues with the winding. However, based on the surge wave shape, we know that there is a significant difference in inductance in B and A as compared to C. Since this fault is not an insulation weakness but instead a now permanent short, the P2P EAR shows a stable waveform. For the EAR result to trip the test, a change must occur. If the shorted windings are hard-bolted faults, there will be no change. As this shows, even though there was no change, so no EAR trip, there was significant difference in inductance between phases. Hopefully, the resistance imbalance would have seen this. Big change in resistance without interrupting current flow could cause this. If a lead were to become loose, the voltage/amplitude of the waveforms would be different and no difference in frequency. This is same motor after another test. This one requires knowledge of the wave movement during the test. The erratic C phase was stable, then it went unstable. This was a sync motor, and the rotor winding was not shorted out. Always short out wound rotor windings when testing stator windings. If not, you can high pot the rotor windings and fail them. A shift to the right shows an increase in capacitance or inductance. What type of scenarios can you think of that would add capacitance or inductance into the circuit? For example, adding the ground lead during the surge test would cause this type of result. As a general case, rotor rotation could cause a shift to the right. This lesson we will consider the test results and decide whether it is best to accept the test result and move on, or should we consider the result an indication that deserves further investigation. You decide. Good or bad? When leakage current is very low, we would normally ignore the doubling rule. Like when leakage is 0.04 microamps and below. However, this can be significant, and I believe I would investigate this and treat as trouble. Can be in wiring box. Move on or investigate. The nonlinear result can be explained. The drop is due to scale change. Good or bad? Okay, that was easy, or is it? Move on or investigate. The nonlinear result can be explained. First 2 points included absorption current due to reverting to dA rather than allowing a full pi. Same motor after a full pi. Move on or investigate. Investigate. Move on or investigate. Move on or investigate. Move on or investigate. Here we tested at starter. Here without motor, just motor lines and starter. Here cable only. Here contactor only. And motor only. Step test of motor, so in this case we had to fix all components, starter, cables and replace motor.